Okay guys, welcome back. This video is basically last part of our lecture, a complete lecture about the two-way slab, its complete introduction and all terminologies and solving some numericals, and now we are heading towards the direct design method, DDM, right? And in this video we will discuss direct design method in detail. We will try to understand it, and then we will solve a numerical to completely understand the design and analysis of two-way slab without beams. Okay, before this video you need to watch the two other videos regarding the shear behavior of slab to a slab uh, with beams and without beams, right? And before that, in another video where we solved the minimum slab thickness requirement in example 2 and example 1, right? Slab thickness required. And before that we also understood different terminologies, for example the rigidity, which is the stiffness ratio, right? And other parameters just like the column strip, middle strip. You can see what is column strip, what is middle strip, what is a panel, what is A, B, C, D, and all other details. Okay, so you need to watch those videos before understanding this one, and then you can watch this video and make your understanding complete in a way to how to analyze and design a two-way slab with direct design method. Okay, so starting the lecture, analysis of two-way slab by the direct design method. The direct design method is an approximate method established by ACI to determine the design moments in the uniformly loaded two-way slabs. Okay, to use this method there are some limitations. What are the limitations? Number one, there must be minimum of 3 continuous spans. So there should be 3 spans and that are to be continuous. The panels must be rectangular, and the ratio of the longer to the shorter span within a panel must not exceed 2, right? Which is the requirement of two-way slab. Adjacent spans in each direction must not differ by more than 1/3 of the longer span. Okay, so if one span is 20 feet, then the adjacent span should not be less than what you say 12 feet. Okay, because 1/3 of 20 is around 6.33, so it should be 13 or something. Columns must not be offset by a maximum of 10% of the span length, right? The offset of columns should not be more than 10% in the direction of offset from either axis between center lines of successive columns. All loads shall be due to gravity only. There are no lateral loads, and loads must be uniform, and the ratio of unfactored live to unfactored dead must not exceed 2. Okay, if beams are present along all sides, if there are beams, slab with beams, the ratio of relative stiffness of beams in two perpendicular directions, that is the ratio in the longer direction to shorter direction, must not be less than 0.2 nor greater than 5. So these are the limitations that need to be addressed before starting the analysis of two-way slab by direct design method. Now, before going to the direct design method, let me just give you a brief description graphically, and then we will see it numerically and in detail, right? So let's suppose this is a grid, right? A grid of a building where there are 4 spans in shorter direction and 5 spans in the longer direction. So this direction is the longitudinal direction, and this direction is the transverse direction. Okay, and please keep in mind that for the sake of understanding I am just taking the longitudinal direction. So we need to revise those terminologies that I already explained in the previous videos. Let's suppose I am taking a frame in longitudinal direction, right? This is a frame. Please keep in mind that this is not a panel, this is a frame. So what I call it at this frame, this is, for example, these all are the interior frames, and the remaining this are the exterior frames, right? So the interior frames have two column strips and two middle strips, and the exterior frame has one column strip and one middle strip, right? This is the only difference. There are no other difference between interior frame and exterior frame. That is, the interior frame is twice of the width of the exterior frame, because the movement from this point, the loads from this point will go to this column center line, and the loads from this point onward will go to the this column center line, right? Now if we consider that strip, right, this exterior frame, now within this exterior frame there are different panels. For example, this one is exterior panel and this one is interior panel, and this one is also interior panel, this one is also interior panel, and this one is exterior panel, right? So there are two exterior panels and three interior panels in this interior frame, right? Now if I consider this interior panel, what I have to do is I need to find the moment. This is the most important thing, that for a single panel there should be a single M naught. This M naught is for this entire panel, and I need to distribute this M naught throughout the panel depending upon the stiffness of this panel, because if you can see that the stiffness of this panel, the stiffness is lesser at this point and is maximum at this point, right, because of the presence of the columns. So the distribution of the moment in the longitudinal direction as well as in the transverse directions depend upon many factors, and this is what direct design method is really about. So we take interior panel and we've just determined the M naught. Now the next step will be to distribute the M naught longitudinally. See, this is the longitudinal direction, and the portion of the M naught will be will goes to M negative, which is the negative moment at the supports. See, these are the supports, the columns, and portion of it will goes to the center, where we call it as M positive. So that M naught, which we just determined in the previous step, is now distributed or divided into M negative and M positive, right? Now we have to further divide or distribute these movements in perpendicular direction, in the orthogonal direction, right, in the shorter direction. So this was our panel, right? Let me show you. So in this frame, the interior frame, for example, if you take this as a center line of the column, so this one is the column strip, half of the column strip, and this one is also half of the column strip. So these two makes a complete column strip, right? And this one is half of the middle strip, and this one is half of the middle strip. So summing them up, adding them up will give you a complete middle strip, right? So then you have to distribute those moments. For example, if you take those M negatives and M positive and you distribute them among these middle strips and column strips, and you will get a complete distribution of your bending moments into this moment. So that M naught will now be distributed throughout the panel, and you have to design for this moment. Now coming to understand these things theoretically, so the total factored static moment M naught is equal to Qu, where Qu is the load intensity in kip per square feet, right, because it is slab. Qu L1 square divided by 8, right? This is the maximum positive bending moment, where L1 is the span length, right? Now if the beam is fixed at both ends or continuous with equal negative moments at both ends, for example, this is the fixed beam and this is continuous with equal negative moments at both end, at A and B, then the total moment m naught will be equal to m positive. So in this case, this m naught is equal to this m positive, right, plus m negative, this m negative. So m naught will be equal to m positive plus m negative, which will be equal to QU L1 square divided by 8, right. And what is L1? You already saw it here. The L1 is the span length. Now if the beam AB carries the load W from a slab that has a width L2 perpendicular to L1. Now we are considering slab where you know that the perpendicular direction of the slab is L2. So in order to take the intensity into account, you have to multiply this intensity QU with this direction L2. So the load intensity in this case for the slab W will be equal to QU into that perpendicular direction L2 into the same formula L1 square divided by 8, right. In this expression, the actual moment occurs when L1 equals the clear span between supports A and B. So when L1 is equal to Ln, then we will get the actual moment. So if the clear span L1 is denoted by Ln, then this equation m naught will be equal to QU into L2 into Ln square divided by 8, and this is the equation presented in ACI section 8.10.3.2, right. This is our equation 10. The clear span Ln is measured face to face of supports in the direction in which moments are considered, but not less than 65% the span length from center to center of supports, okay. So it is a clear span and not the center to center, but it should not be less than 65% of the center to center length. The face of the support where the negative moment shall be calculated is illustrated in figure 11. This is figure 11, where you can see that in case of this where you have to provide, for example, it is a case of square column. So you have to take moment at a distance of 0.175 ln, and in this case you have to take it at a distance of a by 2, right. It is a corbel type structure, so the length of the corbel divided by 2, right. And for the square column and circular column, it is the same. Now the length L2 is measured in a direction perpendicular to Ln and equals the direction between center to center of supports. We already know that. The total moment m naught calculated in the long direction will be referred here as m naught long, and that in the short direction will be m naught s, okay. Once the total moment m naught is calculated in one direction, it is divided into positive and negative moment. I already explained these things, right. M naught is equal to m positive plus m negative. Then each m positive and m negative is distributed across the width of the slab between the column and middle strips, and I already explained these things in graphically, right. So there is no need to get confused. Now how to distribute the m naught into longitudinal direction, that is m positive and m negative. So in a typical interior panel, the total static moment m naught, for example, which I took into consideration, this is the interior panel, right. For example, let me take you, this is the case, okay. So this is a typical interior panel, and you have to distribute this m naught into m positive and m negative, and now it is showing you that how you can distribute that moment, okay. So the total static moment is divided into two moments, positive and negative. The positive equals 35% of total moment and the negative equals 65% because of the stiffness of the columns present at the face of the support. These values of moments are based on the assumption that the interior panel is continuous in both directions. If you go to the first slide of this video, the assumption said that the panel should be continuous, right, because there are 3 or more panels with approximately equal spans and loads, so that the interior joints have no significant rotation, right. So we are assuming that the interior panel is continuous, loads are almost equal, and there are no significant rotation. Moreover, the moment values are approximately the same as those in a fixed ended beam. subjected to uniform loading where the negative moment at the support is twice the positive moment at the midspan, right. Therefore, if you can see that the fraction of positive moment is 35% and the fraction of negative moment is 65%, right. So they are same in if you are analyzing in longer direction or in shorter direction, so the factors remains the same. So for the interior panel you have distributed your m naught into m positive and m negative, right. If the magnitude of negative moment on opposite sides of an interior support are different, so if the magnitude of moments are different, for example this m naught is different than this m naught, because of unequal span lengths the ACI code specifies that the larger moment should be considered. So for example if this m naught is 100 and if this m naught is 80, you have to take the 100 value, right. Now again they are showing you that this is EP, the exterior panel, and this is IP, the interior panel. Okay, the interior panel, its bending moment diagrams in both directions are presented. This is the bending moment diagram of the exterior panel. For the interior panel we already discussed the values of m positive and negative. M positive will be 35% and m negative will be 65%. However, in the case of exterior panel, as you can see that if the exterior support is a simply supported or is it roller or hinge, just like in the case of wall, then this point or this support will not take any bending moment, and MP, the positive moment will be greater in this case, and this will be here it was 35% and here it will be 63%, and the first negative bending moment at first interior face will be 75% of the total moment, and it is again greater than 65%. These are just because no moment has been carried by this point. Okay. In an exterior panel, the slab load is applied to the exterior column from one side only. I already explained it. See, if at this column there are no loading from this side, right. However, when you consider this panel, the loading from this side and this side are almost same. Consequently, there will be an increase in the positive moment at midspan and in the negative moment at the first interior support. I already explained it here, right. The magnitude of the rotation of the exterior joint determines the increase in the moments at midspan and the interior support. So the magnitude of rotation of the exterior joint will determine, and it depends upon the type of support. Okay. For example, if the exterior edge is a simple support, as in the case of slab resting on a wall, the slab moment at the face of the wall there is 0. So there will be 0 bending moment. The positive moment at midspan can be 63% of m naught and negative will be 75% of the m naught. These values satisfy the static equilibrium equation m naught is equal to mp plus half mn. So when you put the values in it, the static equilibrium is satisfied. In a slab column floor system, there is some restraint at the exterior joint provided by the flexural stiffness of the slab and by the flexural stiffness of the exterior columns. According to ACI 810-4, the total static moment m naught in an end span is distributed in different ratios according to table 2. This is the table 2. Here you can see that if the exterior edge is unrestrained, for example a roller support, then the exterior negative factored moment is 0, just like we just saw it here, right, the 0, and here as well this 0, right. So this is the case, but when it is fully restrained, for example a very stiff beam and column are present there, then it will get a 65% of the total m naught, and things between them, so you can see that the percentage varies from 16% to 30%, right. Similarly, the positive factored moment 0.63 for the unrestrained, because there at this point there was no bending moment in the exterior negative face, so the exterior extreme most support. Okay. Therefore, most of the moment was carried by the positive and negative, first negative. However, if it is fully restrained, then you can see that the share of the positive bending moment reduces, and it works like that. Okay, also the shear as compared to this case reduces, and these cases continues with different conditions. For example, if the exterior edge is slab with beams between all supports, or slab without beams, with edge beam and without edge beam. Okay, so these are all different cases you can consider while solving your problem. Now the moment coefficients in column 1, this is column 1, right, for an unrestrained edge are based on the assumption that the ratio of the flexural stiffness of column to the combined flexural stiffness of slabs and beams at a joint. This is the ratio of flexural stiffness of column to the flexural stiffness of slabs and beams is equal to 0. So here restrained it is 0 and fully restrained it is 1. Okay, so it is based on this assumption. This is figure 14, which it was describing here along with the table 2, where you can see that if it is no restraint, so their bending moment is 0 at the outermost support, and it is 63% positive and 75% negative. However, when it is fully restrained, then these two are resisting 65% and this one is resisting 35%, and different cases as we discussed in table 2 as well. Okay, so the coefficients of column 2 are based on the assumptions that the ratio is equal to infinity. I mentioned here 1, it says it is infinity. Okay, the moment coefficients in column 3, 4 and 5 have been established by analyzing the slab system with different geometries and support conditions, as I mentioned here and as well as here, right. Now we have distributed the moment in the longitudinal direction in positive and negative. After doing that, just like I presented graphically, that once we get this moment, these m positives and m negatives, then we have to distribute them in the transverse direction, right. And to do that, we need the percentage of each strip. For example, this column, this middle strip and this middle strip and this column strip and this column strip, taking how much percent of the moment. So when we go to the longitudinal moment values, m negative and positive, mentioned in the previous section are for the entire width of the equivalent building frame, right. This frame width is the sum of the width of 2 half column strips and 2 half middle strips of 2 adjacent panels, right. The transverse distribution of the longitudinal moment to the middle and column strips is a function of the ratios L2 to L1. Now alpha F is equal to beam stiffness divided by slab stiffness. Please keep in mind, now we are talking about the stiffness ratio of beam to slab. Okay, if there are no beams, then this will be equal to 0, and if the beam is very stiff as compared to slab, then it will go as much high, depends upon the values. There is another factor which is called beta T, which is equal to torsional rigidity of the edge beam divided by flexural rigidity of a slab of width equal to beam span length. Okay, so where C is equal to this C equal to torsional constant, and it is determined from these values, where x and y are shorter and longer dimensions of each rectangular component of the section. So now just consider it as I already explained it. The half middle strip and half middle strips are to the center of the towards the center of the panels, and column strips are along the length of this center line or column line of this frame, right. So this is your negative and positive moment distribution, which we have done in previous step. You have to divide this, for example, moment in case of transverse distribution, the whole negative moment at the exterior edge will go to the column strip and nothing will go to the middle strip. Because of the stiffness, this portion will get all of the moment and there will be no bending moment assigned to these portions. Okay, the next one is this center or the positive point where the bending moment, for example the portion of bending moment, and let me show you the positive moment at the middle. Its 60% will go to the column strip and its 40% will go to the middle strip. And similarly the negative moment at the first internal support, the negative moment 75% will go to the column strip and 25% will go to the middle strip, right? And the same will be continue with the internal panels as well. So the percentages of each design moment to be distributed to column and middle strips for interior and exterior panels are given in tables 3 to table 7, table 3, table 6, table 3, table 4, table 5 and table 6. These are presenting and the explanations are given here. If you want you can pause the video here and you can read it out, but let me take you to these tables. Percentage of longitudinal moment in column strip, right? And this is for the interior panel. Please keep in mind that table 3 and 4 are for the interior panel and table 5 and 6 are for the exterior panels. And this alpha f1 which you just found out that it is the ratio of the stiffness of beam to that of the slab. So if it is 0, then these will be the distributions depending upon the aspect ratios L2 to L1 for the negative moment, and these will be the ratios for the positive moments, right? So if it is 0 and if it is greater than 1, then these will be the distributions of M negative and M positive in the transverse direction, right, to the column strip and middle strip. And this is the percentage of moment in two-way interior slab without beams, right? So longitudinal moments in one panel is 65%, the negative moment is 65% and positive is 35. We already discussed it. Now this 65% will be distributed to column strip and middle strip in a way that 75-25, and this positive will be distributed into 60-40, right? So this is the distribution in the without beams slab, interior slab, right, where alpha 1 is equal to 0, alpha f or alpha f1. Now and the value of m naught is also mentioned here. Similarly, you can read out for the external strips for example the negative moment at exterior support, at midspan and first interior support. So the different values, for example in this case beta t is also mentioned, and when you read them for different aspect ratios you can find it, right? And similarly the table 6 which provides you that for example in the case of negative moment at exterior support, 100% will be taken by the column strip and nothing will be taken by the middle strip. This is the case where both alpha f1 and beta t is equal to 0, which means that no beams are present at all. So if you want to read this text, you can just pause this video and read this text. This will help you out. This is also some explanation to that. Now ACI provisions for effects of pattern loadings in continuous structures. The maximum and minimum bending moments at the critical sections are obtained by placing the live load in specific patterns to produce the extreme values, right? Because placing the live load on all spans will not produce either the maximum positive or negative bending moments, and it will cancel out each other's effect. So the maximum and minimum moments depend mainly on the following. Number 1, the ratio of live to dead load. Okay, a high ratio will increase the effect of pattern loadings. The ratio of column to beam stiffness, a low ratio will increase. Here the high ratio will increase and here a low ratio will increase the effect of pattern loadings. And third one, pattern loadings. Maximum positive moments within the spans are less affected by pattern loadings. To determine the design factor moments in continuous structures, ACI specifies the following: when the loading pattern is known, you are sure about the loading pattern, then the equivalent frame shall be analyzed for that load. Okay. Number 2, when the unfactored live load is variable but does not exceed 3/4 of the unfactored dead load, that is Q live is less than or equal to 75% of Q dead, or when all the panels is almost loaded simultaneously with the live load, it is permitted to analyze the frame with full factored live load on the entire slab system. But apart from these two conditions, for other loading conditions, it is permitted to assume that the maximum positive factored moment near a midspan occurs with 0.75 of the full factored live load on the panel and alternate panels. So, for the maximum negative factored moment in the slab at a support, it is permitted to assume that 75% of the full factored live load is applied on adjacent panels only. Factored moments shall not be taken less than the moments occurring with full factored live load on all continuous panels. To summarize it, first check the limitation requirements, then determine, here it is saying that determine the minimum slab thickness, and different formulas are given and we have solved 2 examples on that as well. Calculate the factored load, right. Now check, first you have to determine, now check the slab thickness on the basis of one way and two way shear. We have a separate video on it, you can check it out. And calculate the total static moment m naught. This is that important m naught which then you have to distribute longitudinally in m positive and m negative and transversely into column strip and middle strip. See here. And that will be it. In the next video I will explain this example in a detail. So see you in the second part of this video. Thank you very much.